Okay. So, back to development. We started off last time and we were talking about these debates or discussions, right, that are happening. We left off with active versus passive. So let me get there. All right. So, in an active versus passive, the debate or discussion is, what kind of a role does the child, the individual, play in its own learning, in its own development, right? So if we talk about passive, we're talking about that the environment and genes, the two things we talk about with nature and nurture, are sort of driving development, the experience that the child is undergoing, right? So we talked about whether or not a parent's really encouraging the child to walk or not walk might speed up that development. Children are going to learn to walk regardless because of the genetics, and we'll talk a little bit more about that today, right? But what is the active role, right? So examples we talked about, right? If a child's parents reward them for keeping their room clean, right, or making their bed, that's going to influence the development of whether or not they're going to continue to do that, right? We talked about different genetic influences. Who can think about some development, human development that happens that where active, where what the child is doing plays an important role in that development? Yes. Social skills, right? That's a great example, right? So how a child interacts with other people is going to influence and shape their development of those interactions, right? Children may, during language development, ask to be read to, or ask for, what is this? What is that? Trying to learn words, right? And then social dynamics, right, is something that we learn. And so these things, particularly the active, right, are things that can be heavily influenced by, obviously, our environment, who you're interacting with and how you're interacting, and things like culture. Right? And so we can talk about different cultures have different social dynamics and ways of body language and eye contact and just how you greet people. Right? All of that is very culturally influenced. All right, cool. So, real quick, get a piece of paper. I'm going to have you turn this in at the end of class. We have two different sort of thought paper things today. So real quick, 3 questions. From birth to 18 years old, what is changing? Do like 2 sentences for each of these. We're going to be quick about it. Are you the same from when you were 15 years old to now? Your age now. And what changes between now and how you think you'll be at 7? So 2 sentences for each of those. So we're going to focus a lot on development that's happening in the, childhood through adolescence to about 18 years old. At 18, we kind of start to talk about people being adults, right? The development has really slowed down. But I think it's important to think about this last question, right? That a lot of things can develop, there can be a lot of changes between 18 and end of life, right? 70, 80. And so we need to talk about lifespan development, not just childhood development as well, right? So keep that in mind. Today we're only going to talk about childhood development, but we'll get there. But just recognizing that's not the only place and time that development is happening. Okay? All right, so today we're going to go through some phases of growth in terms of sort of separating that out into 3 phases of prenatal, infancy, childhood, adolescence, and then we'll wrap up talking a little bit about motor development, fine motor development, and gross motor development. All right, so prenatal, focusing on prenatal phases. There are 3 sort of major, sort of definitive phases. So we have a very early phase right after conception, right after fertilization. For the first 2 weeks is called the germinal stage. And this is where we're having cells multiplying, we're growing growing to an embryo. Right? We're starting with a zygote and growing to an embryo. And so we're having very, very rapid development up until about week 3. Then at week 3, we transition into an embryonic phase, and that embryonic phase lasts until we reach the fetal period, which is about week 9. And so we have this very early sort of embryonic phase where the fetus is developing, and then once we reach that fetal period, then we're having more finite sort of developments that are happening, right? Threshold of viability is somewhere around 23 to 25 weeks, where that fetus now can survive if it's born prenatally outside of the uterine environment. Although that can be very challenging. We've gotten really good in terms of medicine and being able to support early childbirth, but there still are some major drawbacks to early birth. This first, we're going to talk a little bit more about what's going on in these very first weeks. This is the germinal stage tends to be less susceptible to outside influences, which is good because most people don't know that they are pregnant within the first couple of weeks, right? And so they may not be very careful about drugs or nutrition or other toxins that they may be that could harm development that they may be in contact with. However, at week 3, we start to get development of the central nervous system, and that is when we actually can have a significant effect of these teratogens. And then throughout development, there are some sensitive phases where drugs and other toxins or malnutrition can influence that. And in fact, there's sort of a newer field of medicine, of study, that's looking at what we call fetal origins of disease, so that actually when a developing fetus is exposed to sort of extreme conditions, either extreme stress in the mother or malnutrition, that can then set up the physiology of our body to influence us throughout the rest of our lifespan, particularly in adulthood, where there's been some studies that have looked at, for instance, people that were born when in times of famine, right? Where for no reason of their own fault, mothers didn't have great nutrition. And then looking at, particularly there's a big study that looked at World War II and babies that were born during periods of famine in World War II. And now those people are in their 70s, 80s, and they can look across their lifespan and they have a much higher rate of things like diabetes and some other metabolic disorders that we think are associated with the fact that they were in that sort of malnutrition environment. Stress is another one. So when there's a lot of stress during development of the fetus, it sets up that developing stress system within that individual to be sort of hyperactive, which in sense makes sense in some case, because you think about if an animal, let's just say, let's get away from people, but just say an animal is in a very stressful environment while they're pregnant, it's likely that the offspring are going to also be in that stressful environment after they're born, and so having their stress system be sort of hyper-vigilant might be a protective thing for them, right? But in people, that becomes problematic. All right. So, physical development happens in sort of spurts, and so we have this big development that happens in infancy, where we develop from an infant sort of shaped body into more of a childhood body. And then there's another big burst of development that happens in puberty, which is sort of too mushy. So while we do have this gradual, remember we talked about continuous versus discontinuous, so we have this continuous developmental growth until about age 18 or so. But there can be spurts of growth, changes in the rate of that gradual growth that happen within that period. The growth also happens in a certain pattern. It happens from the top down with the head developing first. So you can see the head is oversized in infants, right? And it also, we see a center outward sort of growth. So we see the trunk developing faster than the hands and legs are. So sort of two patterns of top down and center outward growth that's happening in infancy. All right. From birth to about age 5, there's massive physical growth. And there's also massive nervous system growth that's happening at the same time. And so at birth, while the brain looks sort of adult-like, there are not as many neurons, so we're going to increase the number of neurons. And more importantly than increasing the number of neurons, so the number of neurons increases pretty dramatically in the first 3 months postnatal. But what do you notice happens between 3 months and 15 months between these pictures? What do you see a lot more of? I don't even know what I'm looking at here. So if we're talking about these are neurons, right? With the different parts of the neuron, right? And so we can see more somas, more cell bodies here. What do we see a lot more of here? Connections, right? And so synaptic connectivity is really increasing throughout infancy. What does that synaptic connectivity represent? Memory can represent memories. It represents learning in general. Learning in general. So infants are learning lots of things. Maybe not lots of semantic information, but lots of other things. How to do stuff, how to react to things. Well, I guess trying to.
Maybe a tough question. But at 3 months, are they capable of learning stuff that just happened? Or is it that they're just not capable?
Yeah, so there are some limits on the capabilities of learning, right? And so sometimes we have to have further development of the brain in order to allow certain learning to happen, right? And we'll see that sort of in our example with the motor system, right? Because we have to develop the ability to control control our muscles in certain ways, and that's what dictates that timeline on when certain motor functions start to come out. All right, so if we look here, so if you look up here at my video, that started at day 15. So this is after that germinal stage. We're in the very beginnings of the embryonic stage. And very early on, we see development of, second embryonic week, we start to see development of this neural plate that is going to become a tube. So this plate sort of invaginates and seals around and goes from being a neural groove into what we call the neural tube. So these neural folds sort of connect with each other. And so by 23 days, we have formed this neural tube, and these somites, these things on the side, are going to be what is going to develop out into our peripheral nervous system. And the neural tube is going to be what develops into our central nervous system, the brain and the spinal cord. So very early on, within 3 weeks of conception, the central nervous system has started forming. And this is a particularly critical time that from about this, really the second week of pregnancy, from 15 days to 23 days, that this proper development can be susceptible to influence of harmful things and not having proper nutrition. So the sort of sequence of this is we have this neural plate that forms into a neural tube, and that neural tube then is going to be our nervous system, both the central brain, the spinal cord, and the peripheral. All right, so every year about 2,500 babies in the United States alone are born with neural tube defects, the most common of which is called spina bifida, where that neural tube doesn't seal properly all the way and from going from a groove into that tube problem, right? And these these deficits can start as early as day 10, but have that sort of critical period through the teen days up until about day 28 or so, right? So for that second half of the first month of pregnancy. It turns out that folic acid, which is a nutrient, is very important in guiding the formation of that neural tube. And deficits in folic acid, not having enough folic acid, result in things like spina bifida and some of these neural tube deficits. The most common form of, or most common reason that we have these neural tube deficits. Calcium and iron are also important nutrients in pregnancy, but really this folic acid is one of the most important. So, how do most people find out that they are pregnant? Missing your period, right? And so when is the maximum time for fertilization? When does most conception happens at ovulation, which is about 2 weeks before menstruation, right? And so most of this development, or this critical period of development, is likely happening, unless you're trying actively to get pregnant and taking prenatal vitamins and being very careful, then a lot of this can happen before you're even aware that you need to be concerned about this sort of stuff. And so, because of about half of the pregnancies in the US are not planned, or not people trying to actively get pregnant, the FDA recommends that women that are sexually active and in reproductive years get at least 400 milligrams of folic acid, right? And that's usually not a problem. They actually add folic acid to things like bread. So if you look at a loaf of bread, it'll say sometimes enriched. If you look at the back, it'll actually say as an ingredient that they've added folic acid to that. This is one way to try and make sure that people are getting enough of this very important nutrient for this development that happens often before people even realize that they're pregnant. All right, so at 3 weeks, we can see those 3 sort of major divisions that we talked about of the brain. They're not fully developed, but we can see that there are regions that are going to be the hindbrain, the midbrain, and the forebrain. And so as the brain develops, up until about 11 weeks, now the forebrain, that cortex, right, has expanded and become bigger than both the midbrain and the hindbrain. So here, at 3 weeks, they're all about the same size. The forebrain is undergoing some rapid growth, more rapid growth than the rest of these parts. Becomes proportionally larger. Also, if you notice, right here at 15 weeks and 24 weeks, what does the brain look like compared to 41 weeks old? What do you see that's different about this brain and this brain? Smooth versus all of these grooves. And so the forebrain is expanding so much. We're creating so many neurons and so many connections that it fills up the inside of the skull and has nowhere to go. And so in order to keep developing, it starts to push inward and create these grooves where down at these grooves there's more cortex. It's a way to expand the surface area beyond the size of our skull. Our skull limits how physically big the brain can be. And so instead of staying smooth like this and stopping development, as it continues to develop, it starts to create these grooves and creates more surface area. And as I mentioned, a newborn's brain has a lot of the same physical characteristics. You know, cerebellum, temporal lobe, frontal lobe. You can see all the different areas. It looks very much like an adult brain, even though it's not fully developed. There's connections haven't developed. Right? But physically, it looks very similar. Development of the brain continues. So by the end of childhood, around pre-adolescence, around age 10, the brain is pretty much set up in an adult-like state. But it continues to develop in more subtle ways throughout adolescence and into early adulthood. And one of the ways that this happens is that we get a decrease in gray matter and an increase in white matter in the brain. That increase in white matter there. So what is, when I say gray matter or white matter, what is the white stuff in the brain? What did we say that was? When we showed a picture of the brain cut in half, and I said, here's the corpus callosum, it's white. Why is it white?
There's no blood in the brain.
There's no blood in the brain, okay. Yeah. So what is the corpus callosum? It's the wires that connects the 2 sides of the brain, right? And then, I mean, there's another time that we showed a brain like cut in half like this, and I said, here, you can see like the cortex is all kind of gray, but inside it's all white. And what does that white represent? If it's connections. What part of that neuron forms the connections? What part of the neuron is the wire part? The axon, right? And what's around the axon? Myelin sheaths, which are fat cells. That's the white part. It took a long time to get to that, right? So the white part is connectivity. So what's happening in adolescence is our brain is becoming more connected. Really what's developing there is we're decreasing the gray matter, the actual dendrites and soma areas, and increasing the connectivity between areas. So if you think back to your ability to sort of reason and make decisions when you were 10, You had the ability to do those things, but you weren't as good at it as hopefully you are at age 18. Right? And so, particularly this area here that we call the orbital frontal cortex, so this is I think this is age 5, and this is age 18. And so we see this red and yellow, which is not very good connectedness. And then we see this purple and blue and green, which is more connectedness, has increased in that time. And if we look at tasks where we have to make decisions or judgments, you get better at that from age 5 to age 18, and this corresponds with this sort of final development. So your brains are not fully developed until about age 22. And then things are like your decision making is about what you're going to have the rest of your life. Right? All right. Looking at some of the physical phases of growth, getting away from the brain stuff to some of the more motor stuff. In middle to late childhood, we have this slowdown in growth. So about 2 inches in height and around 6 pounds a year. So we have this period, as I mentioned, in infancy up until about 6 years. And then we have this slowdown in middle childhood. And then we hit puberty and adolescence, and there's an uptick there in both height and in weight. And this is when the reproductive systems develop, right? So the reproductive systems are one of the last physical systems to develop. Usually happens earlier in girls, around 12 to 13 years, and boys to hit that puberty level. And this is much earlier than 100 years ago. So 100 years ago or older, puberty was happening around 15 to 16 years of age. And so why is this shifted earlier? And we think that better nutrition has plays in that. It's sort of sped up things, better medical care, less exposure to disease. And there's some question or issue of whether or not there are hormones in the environment that might influence this development. And so, this is sort of, again, getting into our scientific literacy. There's not like super good evidence to support this. And so this is sort of getting into that realm of like pseudoscience, where things get picked up in the media. It's like, oh, there's hormones in cow's milk, and so when your kid's drinking milk, it's actually speeding up their prepubescent development. And the evidence for that is not great, right? But it could play a role. Right? So we need to know more about that. What we're saying. Think about that as a research question. It's very difficult. How would you study that? Whether or not exposure to hormones in the environment changes the rate of development. It's contributing to development. It's something we can't do empirical experiment on, right? We can't expose some people to hormones and not others. I don't exactly. I would say yes, but I'm not an expert in that, so I'm not exactly sure on that answer. The question was, do identical twins do the same time? I think yes, because I think that's more of a genetically programmed, and they're also going through the same environmental exposure, right? So I think that would be true. All right, so we have what we call gross motor skills and fine motor skills. Gross motor skills are the awareness of our arms and legs and the ability to control movement of our arms and legs. Fine motor skills would be more like grasping, things we do with our fingers, more finite sort of control. And these are dependent on a couple of things. One, we have to develop the physical muscles in order to be able to control movement of the arms and legs. And so a newborn infant that's born doesn't have the musculature available to be able to control their arms and legs if they wanted to, if they were able to. So part of this is physical growth of the body, and part of it is, again, experience and active exploration. So the infant's ability to move and explore the environment. And there can even be cultural variations. So this is going to be an example of research that's being done to try and quantify this gross motor development. When does it happen and how does it happen?
It's like the baby's minds aren't really in the pre-programmed, but have to learn for themselves. It's at the core of Esther Thaler's research.
I hope the baby's in a good mood, Dexter.
Yeah, I think she will be. Mom said that she's well rested. She's been fed, so she should be in pretty good shape.
Not many research laboratories are able to travel to the subjects they study rather than the other way around.
Hi. Fine. Come on out. How's the baby?
Doing great.
Good. Take her out to the dance.
All of Esther Thaler's research is designed to catch babies in the act of acquiring some new skill, and then to try and figure out how the babies did it. Her newest research project is on how babies learn to control their kicking while they're still getting used to the idea that they have legs.
Hi.
Back in her lab at the University of Indiana, she's already spent several years exploring how babies begin to use their arms.
Ready? Ready. Go. Madeline.
Baby Madeline, only 3 months old, hasn't yet quite got the idea that arms can be used for reaching.
You can see the interest in her eyes. The problem is, how do they get their arms to do it?
All right, so one thing I want to point out is that these are sensors that are able to measure the amount of movement, the direction of movement, and so we're talking about being able to quantify this stuff. So it's not simply they weren't able to grasp it and now they can grasp it, right? A behavioral description of what they're doing, but we're actually getting data on their physical movement here. And so here she's talking about the connection between the baby being interested in seeing the object and being able to physically coordinate their arms in order to grasp that.
Here they have these two springy things hanging off of their shoulders, and their problem is how to get, first of all, just the right amount of muscle contraction to get their hands up, and then they have to also calibrate the space. They have to know where the object is.
What Esther wants to know is how the babies are doing all this. So that Catholic, for instance, only 5 weeks older than Madeline, now has reaching down to a fine art. Esther videotapes the babies.
Slap his arms up and down. It's waiting for the toy.
Then, from 2 different angles, she can follow exactly how the baby goes about reaching. In slow motion, 4-month-old Gabriel seems to be flailing around almost at random. Here's the route his hand takes before he finally gets the toy. But 7 months later, Gabriel reaches out confidently, and his hand moves smoothly to its goal. So while all babies finish up reaching in the same way, they each get there by their own often circuitous route, suggesting to Esther Thaler that how to reach isn't simply programmed in our genes.
Good girl.
And neither is walking.
All right, we'll talk about walking in just a second. There we go. All right, so 2 sort of points about that is, yes, all babies learn how to grasp something, but this shows that how they go about learning that is driven by active learning, not just passive. It's not just genetic, right? And that if we look at 100 infants over the development of this grasping, that they do it in different ways and at different paces. So while the overall pattern is genetically programmed, how it develops is not. All right, so newborns have, so sort of our milestones here of fine motor development. We start with reflexes. Reflexes are things that are genetically programmed that babies are going to do in response to a physical stimulus. If you stick your finger in a baby's mouth, they'll start sucking on it because they have a sucking reflex. Right? Within 1 to 2 months, they start to have visually guided reaching. At 4 months, they're starting to use their hands simultaneously, like we saw in that video clip. Right? And by 7 to 8 months, they're starting to get into sequences of behaviors. So all of this is sort of in response to a stimulus, right? You hold a toy, the baby visually sees it, guides its hand there to grasp it, that sort of thing. At 7 to 8 months, they're starting to create their own sequences, not in response to physical stimuli. And this is when we start to get the transition from crawling into walking. Walking is a very complex sequence. Think about what has to happen in my motor cortex for me to walk from one side of the room to the other. I'm doing things like, I have to pick my leg up, right? I have to put my leg down. I have to pick my next leg up. I have to keep my ankle at a certain angle. I have to balance. I'm swinging my arms. There's this big complex motor sequence to learning how to walk. All of these things are happening. So through the first 1.5 years is like a major developmental motor system, and then from about 1.5 years until early adolescence, we're learning way more finite sequences. How to ride a bike, right? How to do all sorts of, how to feed yourself, right? How to hold a fork, how to write with a pencil. All of these are fine motor skills that develop during childhood. All right. I mentioned this when we talked about sleep, and then we never covered it, and so I thought this would be a good point to mention that sleep changes across our lifespan. Right? We talked about how infants, we have to have that sleep cycle develop, but they spend a lot more time asleep, 16 hours a day in newborns, compared to adults that only need that 7 to 8 hours a day. Right? And so why are they doing this?